section, I believe. Yeah, section 139. Just to go over it again, you got contents over here. Make sure you read through the contents. Make sure you look at the examples. Make sure you attempt to do the exercises. Again, my name is Ron Bannon. This is a draft version of my adaptation of Webster Wells's Advanced Algebra, which dates back to 1904. The PDF document is only being made available to the prison mathematics project participants. But this is the 139th video, so actually more than that because there were some introductory videos. A lot of videos have passed by, right? So the bottom line is this is Wells's closing chapter, all right? And what I mean by closing chapter, he talks about a numerical technique. Now, the first time I read it, he said Newton's method. I thought he meant Newton's method by using derivatives, but he's using a different technique that I wasn't aware of. So I'll go through that, though. But my intent over here is this is a numerical technique. It really depends on your ability to use a computer because it's numerical. I don't want to see people using paper and pencil to do computations for a numerical technique. It just doesn't make any sense. Not nowadays anyway. Now, back in Wells's time, it was difficult. Now, since my first reading of it, I thought he was going to talk about derivatives, but he didn't. But since we talk about derivatives, you may want to consider this technique over here, and we would recommend you read through that. Now, the intent of this lecture over here is not to go through me reading the document to you, but it's to use a computer to do these problems over here. So I'm going to say over here, basically what I do is I give you a picture, I tell you what the method is, and we'll talk about numerically how you do that on a computer, all right? But I put the work down, I put my intermediate answers down, and so how did you get these things over here? I'm using a formula to get those things, and it's tough. If you have to do this by hand, it's a nightmare. I wouldn't want to do it by hand. But anyway, yada, 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 yada. I do it. Then there's exercises. I do a review or a recap of Newton's method. But I'll be honest with you, when I'm doing the exercises, I do Newton's method using derivatives, but I also use Wells's technique, right? It's going to be both are down there. Both are down, right? Both are down. I'm not going to just simply say I'll just do my version of Newton. I should say my version, the version that I've been introduced to in Newton's method involved derivatives. His doesn't. So I do, my introduction to Newton's method, and I do his introduction to Newton's method, and I go through a bunch of problems here. All right, so what I want to do is I want to just, kind of look at the code, and we'll get to that. It's a long section, by the way, right? Get this related Sage code. And what I want to do is I want to, I'm going to pull up my instance of Sage. I'm going to clear the screen. And I'm going to type these commands in. Reset. And I'm just learning over here. X is a variable. This is what we're expecting you to do too if you have access to Sage. And then f of x. And I'm going to put this down for you. F of x, well, they're assigning it. That's an equal sign. I mean, it's assigning x cubed minus 3x squared minus 2x. You know what? I made a mistake. It has to be a multiplication symbol. And sorry about that. It would come back a mistake. So 3x squared minus 2x. What's nice about having code with answers, I can check myself. Hit the return button, no errors. And then I'll say differentiate. So df, I'm making a derivative. A derivative of who? Well, let's see. It's a function of x. I'm going to assign it the derivative, diff, of f of x with respect to x. All right? Hit the return button. No errors still. And then I said x sub 0 is a guess. Now, before I do that, what I'm going to do is I'm going to just plot the function. That's not in the code, but if you've been paying attention, you know how to use Sage to plot. All right, I'm going to plot f of x and see what happens. All right, now it says it launched a graphic viewer, and you know what? I don't like the image. I'm going to close that, and I'm going to, set the x to something different. Okay, watch what I do here. F of x. I'm sorry. Plot. I'm going to change the x now. And I got to remember how to do that. I think it was x min equals minus 5 and x max equals 5. And if I can't remember, I'll have to look it up. There it is. So what am I seeing? I'm seeing a bunch of roots now. I'm seeing a root over here, a root over there, a root over there. Now what I want to do is I want to find one of the roots. Now it appears what they're looking for is the root over here, which is 1 point something. All right? So what I'm going to do over here, I'm going to set x, whoops, I'm going to set x0 to 1 point something. And over here, say 1.2. Now, someone says, why would you do it? Why don't you try your own number? I'm just learning. All right, now what I'm going to do is I'm going to say n, and n stands for Newton's method using derivatives. I'm going to say nx is a function, and what is it going to be? X minus f of x divided by, well, we defined a function df2, right? Gee, that worked. And I'm going to say x1 is equal to n of x sub 0. And what I want to do is I want to display x sub 1. And I got that number over there. All right? Now what I want to do, I want to do x2. By the way, the same numbers on the computer. I want to do x2 now. And you notice the machine's doing all the work for me now. I have to type though. So it's going to be x1 now. And what do I want to do? I want to display x sub 2. All right? I'll do that. And I think I'm doing okay. I think I'm ready now to go back in the notes and try. Well, it's the same. No, it's a different problem, isn't it? Yeah, it's a different problem. So what I want to do is I want to try this problem here. Now, someone says I'm not ready. Well, you may not be. But I want to type this in and see if I can remember. So f of x is equal to x cubed minus 2 star x squared minus 23 star x plus 70. Oops. No error. I want to do the derivative now, if you recall, remember? And I want to point out what I mean by that. Remember I did the derivative? How'd I do that? I defined the new function. So df of x is going to be assigned the derivative diff f of x, and I'm going to differentiate with respect to x. Now I want to point out the next thing I would do is define Newton's function. And I think I did that before. I'm going to pull it up again, just to use my arrow keys to get it. I would put that in next. All right, let me do that. That's done. Now let me go to the next thing. And before I do that, I want to point out, I want to plot it. What do I want to plot? I want to plot f of x. Now I don't know what it looks like, but I'm going to do this over here, and it opens up. And I'm not really seeing much over there. So I'm going to close that out, and I'm going to, plot again, but I'm going to change the x min to 10 now, minus 10. Right? We did that before, right? But now I'm doing minus 10. And it might be bad on choice. I don't know. Let's see what happens. X max equals 10. Well, that's better, isn't it? So someone's looking at it. I got to be honest with you. It only looks like there's one root there. So if I look at it, the positive, there's no positive root. So it just seems like there's a root at around minus 5 point something. Right? So I'm going to close that out. I'm pretty much convinced of that. And they said the initial estimate, I'll write this down for you, x sub 0, they're saying make it minus 5.1. Now someone can say use a different number. Of course you can. Right. Now someone says, why did you use that one then? Well, it looked about minus 5 point something. Now what I want to do is just see if I can get these values over here. Not by hand computation, but by using the Newton method. So what do I have to do? Now, if you remember, I got to assign x1 the value from Newton's method, which was n of x0, or x0. And I want to display x1. Now let's hope we do okay. Did I get the same number? Well, I'm not going to read all the digits off to you, but it appears to be the same number. Now I want to see if I get the next one. All right? Let me pull this over so you can see what I'm doing over here. Let me pull this up. I want to see if I get x2 now. All right? Let me pull this over so you can see the screen better. All right. x2 is going to equal n of x sub 1. And what do I want to do? I want to display x2. Let's hope we get the same number. Looking good. Now what I want to do is I want to do x3. Let's put that down. X sub 3 is going to equal n of x sub 2. And I want to display x sub 3. Let's do that. See what happens. I got that number. Let's go again. You notice the numbers are changing though, right? So how do I know the numbers changing? Just look at the last digit. They're clearly changing. What am I going to do now? X sub 4. I'm developing more confidence now. Equals n x sub 3. If you make a mistake in typing, it's not going to blow up. I want to display x sub 4. And let's see what happens. Now what do I notice there? The number hasn't changed. So what is it doing? It's returning the same number. We'd be in an infinite loop now. If I keep feeding it this number, it's going to keep feeding the same number back to me. So I'm going to say that's where I'd stop. All right? Let me point out by that. I'm seeing that number over there. We're going to stop there. So what does it say? No change. So this is the best estimate of the desired root given the precision of our computation. All right? We did okay. All right. So here's the deal. I know this is difficult, but the bottom line is there's another thing in the code. Let me go back to the code. This is Wells's adaptation of Newton's method without using derivatives. I was not aware of that method, by the way, until I read Wells's text. You could type this stuff in over here. It's the same thing we're doing in the notes. What's the point of this, though, is to learn by doing it. So what are we doing over here? Defining a new variable, and we're doing this business over here. Now, granted, if you want to try this code over here, you got to go back and type this stuff in. All right? Because what happened now, I changed the function. So here's the deal. Do this, and then go back over the notes. And I want to point when you go back over the notes, yeah, I do Wells's version and my version. Right now I say, I really should say my version, but my initial impression of what Newton's method involving derivatives, and then Wells's. And when I do Wells's, what I do is I don't write all the work down. I just write down the intermediate results that I'm getting. And you may want to try that, right? You may want to try that. What do I mean by that? Studying the code, seeing if you can come up with that. All right, thank you.